Okay, sorry about that. So yes, this would be considered overfitting over here. Okay. All right. So to sum it up, okay, or actually, I guess, you know, so what should we do, right? How do we balance between our desire to make accurate predictions and also have a model that we can interpret, right? And so, do we ever want this restrictive model, say something like this? So this is a restrictive model where we say, hey, everything needs to have a flat line, a flat relationship, a linear relationship. Our inputs and our outputs need to have a linear relationship, okay? And you might say, well, I don't want that. This is making bad predictions. This doesn't look anything like the true surface. Having a linear relationship with everything is too restrictive. Okay. Well, there might be some occasions where you want to have that restrictive model. Okay. Basically, if your goal is interpretation, restrictive models are a lot easier to interpret. Okay, it's easier to understand, easier to explain. It's a lot easier to just say, hey, in general, as people have more years of education, their income increases. As people have more seniority, their income increases. And in fact, just as a rule of thumb, we'll say every additional year of education, your income goes up $1,000 per year or something. And every additional year in seniority you have, your income goes up $800 a year or something like that, right? And that's just kind of like, that's a simple rule of thumb. We know it's not perfect, but just overall, like that's going to maybe get you a decent guess for something like that. And that's a lot easier than to say like, okay, the true relationship is that as years of income goes up, plug it into this cubic function or something like that to figure it out, right? Any kind of overall rules of thumb that we like to kind of guess and that are easy and are generally, I guess, easier to interpret and easier to explain and easier to understand, right? So a lot of things in life aren't perfect linear relationships, okay, but they serve as kind of just useful ways to make estimates, right? And you can say, in general, as your car gets older, it's going to lose, I don't know, this much value or something like that. Okay. The other benefits for having a more restrictive model is that you're probably not going to overfit. It's hard to imagine this kind of flat model overfitting the data. Okay, its predictions aren't going to be as good, but you're not going to ever have to worry about having some kind of weird overfitting situation like this. Okay. And then the other highly flexible models, okay, will often require lots of data for an accurate fit. So those are some reasons why you would want to go with some kind of more restrictive model. Obviously, in a lot of situations, you want to get as close to the true thing as possible. And that might mean having a more flexible model. And so we'll talk about all of these different kinds of models that are out there. But just know that you'll require lots of data. And so, for our Kaggle competitions that I'm planning, you will have lots of data. So you can use these highly flexible models, because I think the highly flexible models can be fun. But again, they require lots of data, and I would, but I will be providing you lots of data here. Okay. So here are some of the different models that we might see, and they're kind of in this. On one end, you have high interpretability but low flexibility, and on the other end, you have low interpretability but high flexibility, and then you have things that are kind of in between. So your low flexibility but high interpretability are things like your linear regression, linear least squares regression. That's pretty simple. Okay, we have a regularization method lasso, which is basically a even like a more restrictive least squares regression. Subset selection is basically just taking selecting some of the input variables, right? So, subsetting them to fit your model and things like that. And those are all very easy to understand, but they are restrictive, don't have a ton of flexibility. Okay. In between this kind of low and high flexibility and low and high interpretability, you have generalized additive models, which include kind of splines and things like that. And then you have trees, decision trees, are somewhere in between. Okay. And on the high flexibility but less interpretability, you have these tree-based models like bagging and boosted trees. So, one of the most popular machine learning algorithms is XGBoost, extreme gradient boosting. And that's basically a tree-based model where it fits like thousands of trees, like a random, it's basically random forest, but a whole bunch of boosted trees. And it's highly flexible. But if somebody said, hey, can you provide an interpretation for what this input variable does? It's a lot more harder. Okay. You have support vector machines, which basically draw this boundary in this high dimensional space. High flexibility, low interpretability. Neural networks also fall in that kind of class of high flexibility, but you might have millions of parameters in your neural network, and what each of those things mean is a mystery, effectively. Okay. So that was one way to kind of divide our models, is parametric versus non-parametric, or highly flexible and less flexible, or things like that. Or I guess those are different ways two different ways. Another way to kind of divide the models that we'll be looking at is we have supervised learning models and unsupervised learning models. Okay. The things that I've kind of talked about so far have all been supervised learning. Okay. In supervised learning, you have your input values and the output, the response. Okay. And with supervised learning, you kind of have like a target goal. Okay. In that you want your predictions to get closer and closer to the actual values, right? So you have the actual responses, the actual output values, and you say, well, my model is getting better because the predictions are getting closer and closer to what they actually are, right? So if you know your destination, you can keep improving your model to get closer and closer to that destination. And I would say most of the methods we're going to cover in our class will fall under this supervised learning. On the other hand, we also have unsupervised learning. Okay. In unsupervised learning, you only have the X values. There's no output. All right. There's no output value that's recorded. And so you don't know, like, am I getting closer to the true answer? You don't have a way to kind of measure that overall performance. Okay, so you have different ways to kind of measure performance. You don't have a true answer to compare your answers against. You're just kind of looking for internal structure within the data. So things like clustering and dimension reduction fall under unsupervised learning. So clustering says, okay, within our data, we don't really know how each of our values should be classified or anything. So let's just try to form little clusters. These observations are similar to each other. So let's put them together. Okay. And so that's going to be, that's unsupervised learning. Okay. Regarding the supervised learning. So remember, these are answers are recorded, so we know we're getting closer to the true thing, right? It's kind of like, I don't know, sometimes you have answers in the back of your textbook, and you can kind of check, like, did I learn this properly? And you do your homework problem, and then you compare it to the back of the answer in the back of the book, and you go, oh, I got the same answer. Therefore, I'm learning it well. Okay. So these are all kind of supervised learning. You have the answer, and you can see if you're learning it well. Okay. And those supervised learning problems, methods can be further divided into regression and classification. Okay. Basically, regression is where your response variable is a number, and classification is for when your response variable is a category. Okay. So examples of regression problems is, you might say, okay, let's figure out how much a house costs based on different inputs. We're going to put in how big is the house, and how many bedrooms, and how many bathrooms, and what neighborhood is it located in, and when was it built, and based on that, let's predict the cost of the house. Okay. Or you might say, okay, based on I don't know, these values about the customer, right? This is what they purchased in the past, and this and that. We're going to predict how much they're going to spend. Okay. So those are numeric responses, right? The cost of a house, how much somebody will spend. So those would be regression problems. Okay. Classification is, you're trying to predict a category. So, is the email message that I'm receiving, is it spam? Is it something desired or undesired? Okay. Is it, unsolicited, and we flag it and put it in the spam folder, or is it a piece of mail that I do want? Okay. So that's a classification. Okay. Is someone going to default on a loan? Okay. So if somebody borrows money, will they ever have a month where they don't, you borrow money and now you have to make payments every single month? Is there, can we predict if they're going to miss a payment? Okay. And we can say, okay, well, based on their income and based on their credit score and based on this and that, we'll try to predict whether somebody will default or not. Okay. That would be a classification problem. Okay, so, how do we, when we're talking about this supervised learning, and we're saying, okay, this is what my model is predicting, this is the true value. How do we decide if our model is improving or not? Okay, so if the true value is 10 and one model predicts 9 and another model predicts 8, okay, we can say the model that predicted 9 did a better job than the model predicted 8, because the true value is 10 and 9 is closer to 10 and than 8 is. That's simple. Okay. But you might have a data set with multiple values. Okay. So maybe for observation 1, the true answer is 10, and observation 2, the true answer is 20. Okay. And model A predicts 9 for the first observation and 15 for the second observation. Okay. The second model predicts 8 for the first observation, basically a different, and 18 for the second observation. Okay. So which one is better now, right? So model 1, the true answers are 10 and 20, and model 1 is predicting 9 and 15. So the first one's off by 1 and the second one's off by 5. Okay, model 2, the first observation predicts 8 and the second observation predicts 18. It's off by 2 on the first and off by 2 on the second, right? And so, which one is better? Which one's better? Okay, and you guys say, well, the total error for the second model is 4. It was off by 2 and off by 2, and the total error for the first one is 6, 1, and 5. Then we're going to say the second model is better, or things like that. Basically, how do we evaluate this? We want to come up with some kind of unified way, and one of our most common measures of accuracy is mean squared error, okay, or its, you know, related cousin, the or sister, I don't know, the root mean squared error, RMSE, okay. And this basically just says, you know what, take the actual value. If we said the actual value is 10 and the predicted value is 1 or 9, okay, its error is 1 and we square that and we would get, you know, 1 squared. If the actual value is 20 and we predicted 15, we would take that difference 5 and we would square it and we would get 25. All right, so you get, and then you would take the average. So you get 1 and 25, and then so your mean squared error in that case would be 13. Okay, model 2, you know, the true answer was 10 and we predicted 8. So we have 2 and we square that and we get 4. The second observation, the true answer was 20 and we predicted 18. We had a difference of 2. 2 squared is 4 again. So we have 4 and 4 and our mean squared error is 4. So one, the mean squared error is 13. The other, the mean squared error is 4. And we'd say, okay, yeah, model 2 is better because it has less mean squared error. So we're going to, you know, we measure the difference between the actual value and the prediction. And, you know, we square it, okay? One thing about squaring the error is that it punishes larger errors more heavily. So actually, you know, a better thing, we'll say, so we'll say actual, let's say is 10 and 20, okay? And so model 1, let's say we have 9 and 9 and 17, okay? And then model 2 will have 8 and 18, okay? So your errors will be, here we have 1 and 3, and here we have 2 and 2, okay? So the mean is 2 in both of these cases. But then if you do y minus y hat squared, okay, you would have 1 and 4, I'm sorry, 1 and 9. And here we would have 4 and 4, okay? And so the mean, the MSE here would be 5 and the MSE here would be 4. Okay, so by squaring it, this 3 gets it gets punished more heavily, and basically than the 2s. Okay, and another way to think of this, okay, is it better to have, if you have 10 observations, okay, you can have model 1, basically 9 observations are perfect, but observation 10 is off by 10. Okay, so then your total squared error is going to be basically 0 squared plus 10 squared. So your total squared error is 100, right? Because the last observation is 10, you've got a whole bunch of zeros. Okay, model 2, all 10 observations are off by 1. Okay, so model 1, you have no error, 1 observation is off by 10. Model 2, all 10 observations are off by 1. Okay, your total squared error here is going to be 1 squared plus 1 squared, and you got 10 observations, you're going to have total squared error of 10. Okay, so the mean squared error here for model 1 is going to be 100 over 10, and the mean squared error is over here is going to be 1. Basically, when you have mean squared error, it's going to say a bunch of small errors is better than having one big error. Okay, so that's one thing to keep in mind for mean squared error, is one big error is worse than having a whole bunch of small errors. And that's why in linear regression, I'm pretty sure you learned this, that outliers can have a huge impact on the model, because for linear regression, your metric for performance is basically sum of squared errors. You're trying to minimize your sum of squared errors. And so therefore, when you have an outlier, it really tries to fit that outlier, because it really doesn't want one big error. It would rather have a whole bunch of little errors and minimize and not have that one big error. Okay, so that's why outliers have such a large impact on the fit of basically sum of squared errors there. Okay, question 3 on the view quiz. Question 3 is the letter E. So put that down. So this is your third view quiz answer. Question 3 is the letter E. Okay. So when we're fitting the model to the training data, we want to minimize the distance between the actual value and the predicted value in our training data. Okay. But we don't want to just fit the training data perfectly. Okay. What we want is a model that's going to work in the future. Okay. We want to have a model that's going to generalize to the real world, and we want to have the model work on data that it hasn't seen. Okay. So when we trained it, we said, okay, look at these things. And rather than just kind of like memorizing all of the observations, we wanted to establish, some kind of system, like, does it recognize this pattern, so that when we show it a new observation, it can make a good prediction, right? And so that's what we want. Okay. And so the new data that it hasn't seen yet, we call that the test data, right? And there's no guarantee that when you train a good model and you get the smallest mean squared error on the training data, that it's also going to perform well on the test data, right? A lot of it depends on how similar the training data is to the test data. So hopefully the two things are similar, but it also, did your model overfit the training data or not? If you overfit the training data and you said, okay, I want to know what your favorite color is, and based on that, I'm going to determine your height. Okay, if that's part of your model and you got, you say, well, I made really good predictions on my training data based, by taking into account the person's favorite color. Okay, when you bring in the test data and you say, okay, well, here we have a whole bunch of people, and these people, their favorite color was this color, and that their favorite color was that. And oh man, I'm not making good predictions at all. Okay, that could happen too, right? You overfit your training data. Okay. In general, when you have a very flexible model, you can get the metric for your training data really low. Okay, it will fit the training data very well. You put in a whole bunch of predictor variables and things like that. If you have really flexible methods such as splines, you can generate a whole bunch of different shapes and things that can really fit your training data. Okay, but when you then take that model that fits your training data really, really, really well, when you put it on your test data, okay, your test mean squared error, so the mean squared error on your test data could end up being higher, all right? Because you've overfit your data, right? So these are some diagrams that I've taken from our textbook, and let me try to explain what they mean. Okay, so on the left, we're going to see several graphs here. On the left, the black line is the true model. Okay, and then we have 3 models to fit. Okay, the orange line is going to be a straight line model. Okay, and then we have a blue line, a smoothing spline with medium flexibility, and a green line with high flexibility. Okay. And, the blue and the green are a little bit really hard to see. I will try to trace the blue line in red, so it's a little bit easier. Okay, I don't know if you can see that. Okay, so that red line is these are estimates. So the black line is the true. The black line is true. All right. And then we have random data generated around the true model. So basically, so this is all simulated stuff, but we just said, okay, if this black line is the true model, as we put in random, we have data generated from it, and we said, okay, just randomly put in a data point that's higher or lower than the black line. Okay, and we said, okay, here is a red line. Okay, and we fit that. And here is a blue line, and we fit that. And then here is a green line, and that's the really flexible one. Okay, and you can see the really flexible one kind of overfits our data. Okay. This graph over here is the mean squared error for basically your training data and your test data. Okay. The gray is for the training and the red is for the test. And so this one is the linear model. And you can see it's got high error on the training data. Okay. This one is the I guess the spline, and this is the very jagged spline. Okay. So the very jagged spline has the least amount of error between the actual values and the lines. Okay, so when you take the difference between the dots and the actual and the prediction, okay, that one has the least amount of error. Okay, but on the in a test case, okay, in the test data, basically we generated some new data points around the black line, okay, and we said, okay, well, how well does our model fit this new data? Okay, well, the linear model doesn't do a great job. Okay, the spline does pretty well, and then now the really jagged line does poorly. Okay, and so these are kind of the three lines, and theoretically you can kind of try out a whole bunch of different flexibility levels, and if you get a line that's too flexible, you end up getting even worse performance as it gets the performance on new unseen data gets really bad. Does that kind of make sense? What's happening on this thing? This horizontal dotted line over here, this is kind of your theoretic lower limit on the mean squared error that you can achieve on test data. That would be if you achieved the true model. Here you would get that. Okay, so I think I've written that. So the true model is a curved line. The straight orange line does a poor job of fitting the training data. It's inflexible. It has the highest training MSE and the highest test MSE. Okay, the highly flexible green line has very little error on the training data, but but it's overfitting the data, and on the test MSE, on the test data, its MSE is pretty high. And then the blue line is moderately flexible and does a good job, which is kind of this middle one here. And it has a lower training MSE, but it's in second place for the training MSE, but it has the best performance on the test MSE. Okay. So we have this kind of U-shape relationship between flexibility and test MSE. So here's another example. Okay, here the true relationship is in black. Okay, and then we have a linear model in orange, and then a slightly flexible spline in blue, and then a jagged, very flexible spline in green. Okay, and here we see, oh, you know what? The linear model does a pretty good job. the linear model does a pretty good job on estimating the true relationship, and then having a slightly more flexible spline also does a pretty good job. Okay, having a very flexible spline. So again, this one is linear. And then this is the smooth spline. And then this is the jagged spline. So the jagged spline does really good on the training data, right? It's really, because we have these outliers on the training data, it does a really good job on that. And so it has very small mean squared error. But then when we put in new test data, it does poorly. Okay, it does poorly. And here, linear relationship versus smooth spline, you're only getting a little bit of performance increase by having a smoothed out spline. Okay, so that blue line. Okay, so here similar kind of story here, but I'm going to just look at this. The blue line does have the best performing mean squared error on the test data. Okay, but I would say maybe a linear relationship provides the advantage of being really easy to explain. Okay, and so you can say, oh yeah, you know what, the relationship between x and y is that, you know, when x goes up by 10, y goes up by 1 or something like that, right? You start off at 0 and at 2, and then when x gets to 100, you're at 12. That's pretty easy to explain. The true relationship is a little bit more complicated, but you can just say, overall, in general, every time x goes up 10, you can predict y goes up by 1. And that's going to get you just about as good as the flexible spline there. Okay, same kind of story here. Here you can see that the having a straight line relationship does a really, really bad job. Okay, and then having a smoother line does the best, and then having a really jagged line doesn't do as good of a job as having the smooth spline. Okay, and so you can see, you know, we still get kind of a U shape here. It's just that having having a straight line does a really, really bad job. Okay, but on the training data, always, as you increase more flexibility, the training MSE will keep going down and down and down. Okay, it's just kind of like, and I'm sure you saw this for in 101A. In 101A, as you increase the number of predictors, you could always get your R-squared value to be a little bit higher, right? Your R-squared value always got a little bit higher as you increase the number of predictors. But in 101A, I think you learned things like the likelihood ratio test to determine if those predictors were significant or not, and whether you should include them or not. And you also had things like AIC and BIC that had a penalty for having too many predictor values, so that you wouldn't pick the model that just had the highest R-squared value. You would pick the model that kind of provided the right balance between having, you know, good predictive value, you know, a high R-squared value, but not too many predictors. Okay, and that's kind of a similar idea here. You don't, this is reaching the point where you have too many predictors. Okay, you want to have good prediction power, so low mean squared error, but not too many predictors. Okay, and that this concept of more flexibility, but overfitting versus less flexibility, and doing a better job, that's summarized in this concept of the bias variance trade-off. Okay. You know, those previous graphs and the tests versus, you know, the kind of the test data versus the training data, mean squared error shows kind of a, you know, this important trade-off that kind of helps us decide what kind of statistical learning method we should use, and ultimately what model we want to pick, right? You know, the bias versus the variance. Okay. Bias refers to the error that's introduced by modeling a real life problem with a much simpler system. Okay, so the bias is the difference between basically the best your model can do and the true relationship. So let me go back a few slides. This thing, this model is a flat plane, okay? And we're trying to use it to model the true relationship in blue here, okay? There's always going to be, no matter how good we get this, there's always going to be a difference between what a flat plane can do versus the true relationship, okay? And that difference between basically, kind of using this much simpler system of using a flat plane, that's going to be the bias of the model, okay? So, linear regression assumes there's a linear relationship between y and x. And, it's unlikely in real life that, or in the case that I show you, we know that in real life, the relationship is not linear. So there is going to be bias, okay? And if you have a very kind of flexible system, okay, and you think about, how well or either of these things, okay, in kind of the optimal scenario, both of these, like the really flexible spline and the, somewhat smooth spline, might be able to achieve this, the true model perfectly if it had enough data, okay? It might be able to achieve this, right? So kind of in the long run, it might do a really good job, okay? And in general, if a model is more flexible or more complicated or something, it's going to have less bias, okay? The variance, though, is how much does your fitted model change if you had if you had a different selection of random data, okay? If you have a different selection of random data. So if you have a model that's very flexible and somebody went out and collected data on a different day, and they come back and you say, all right, use this really flexible model to fit this new data set, that model might end up looking quite a bit different from your first model, right? Because, if you have, on Monday, you collected data and you say, all right, this is the surface that we have, and it fits it really well. And then on Tuesday, you collected different data and you say, okay, well, here's the surface. And you compare this model surface and this model surface, they might look quite a bit different, okay? And so the fact that one model and another model look quite a bit different indicates you have a lot of variance, okay? And that's an issue. Okay, you don't want that, right? And that's in 101A, you probably had this thing called variance inflation factor, right? VIF, where you have these highly correlated variables. And when you have these highly correlated variables, your estimates of what those what the coefficients are really depend a lot on your random data set. Okay, so let's say you're trying to predict housing prices, and one variable is the number of bedrooms, and the other variable is the number of bathrooms. Okay, and those variables are highly correlated, and depending on your random data, one says, okay, on Monday's data set, you fit the model and you have both bathrooms and bedrooms in there, and on Monday's data set, it says bathrooms are the most important variable and bedrooms are less important. And so the coefficient associated with bathrooms is really high and the coefficient for bedrooms is less, okay? But on Tuesday's data set, the opposite turns out, okay? Bathrooms is less important, bedrooms is more important. Their bedrooms are more correlated with the price than bathrooms, okay? And so the fact that your coefficients can bounce around quite a bit based on what your data set looks like, means you have high variance. And so you actually get better performance if you say, you know what, let's just throw away one of these variables. Let's just throw away the number of bedrooms, okay? And we're only going to look at the number of bathrooms. And that might actually improve your performance because now the number, how much your coefficients vary will shrink a little bit, okay? And so so the fact that depending on which random data set you get, if if it can dramatically affect what your coefficients are, that's probably not a good sign. Okay, that's probably not a good sign. So, so a method that's very flexible could end up changing quite a bit for different random training data, and so you're going to have high variance. Okay. So, mathematically, this can be expressed as this. Okay. This is what is the difference between the actual observation value and our predicted value for that. Okay, so this is the average mean squared error that we would obtain if we repeatedly estimated the true function, okay, using a large number of training sets, okay, and measured the difference between our predicted value and the actual thing. Okay, so this is, why is there an expectation here? Okay, and that's because here we're saying this f hat is subject to the randomness in our training data. Okay, so let's say we have 5 different training sets of data. Okay, and one you fit the model based on training set 1, and then you fit the model based on training set 2, and you fit the model based on training set 3. Each of those models will be slightly different, right? One might have this slope, and model 1 might have a slope intercept of 1 and a slope of 1.5, and model 2 might have an intercept of 0 and a slope of 1.8, and model 3 might have an intercept of 1.5 and a slope of 1.6, right? So you're gonna, each of these, based on your random training data, you might have just ever so slightly different linear regression lines. Okay, and so that's why there's an expected value. So what is your f hat going to be? Okay, and so that can be broken down into the variance and the bias. Okay, the variance, okay, is how much the estimate will change from one training data set to another training data set. Okay, and then the bias is how much this expected value, okay, over all of the different kind of possible training sets, how different is that thing going to be from the true relationship? Okay, and then we have just the overall kind of irreducible error that we can't get rid of, no matter how good our the true relationship, even if we were to model the true relationship perfectly. Okay, and in general, as this bias increases, okay, the variance is going to increase. So so I'm going to generate a whole bunch of these things. The true model is going to be in black, and I'm going to fit a highly flexible model in green and a model with less flexibility in blue. Okay, and so this is just some code that I've generated. So can you see these things? Okay, the blue line. Okay, so the true model is in black. I got random data in red here. Okay, and we said here's a model with less flexibility, and the green model is high flexibility. Okay, here is same true relationship. So you can see the black line is exactly the same. So in all of these, I've got 3 of these plots. Okay, the black line is exactly the same in all 3. The red data, the random data, is different for each of these things. And you can see the light blue line shifts around a little bit from one random data set to another. Okay, and you can see the green line changes quite a bit from one random data set to another. Okay, so overall, okay, this blue line, consistently has a little bit of a tough time, right? It consistently underestimates the black line over here, and it overestimates the black line over here. Okay, because there's a limitation in this model here. So what we see is that the blue line has less flexibility. The green line has high flexibility. Okay, But the model looks relatively stable going from one training set to another training set. Okay, so we have low variance when we look at the blue line. So if we look at the blue line and I go from one random training set to another, that blue line doesn't change very much. Low variance. Okay, but there's a bias. Okay, we can imagine even in the kind of overall, the average of all of these blue lines, there's quite a bit of difference, right? The blue line consistently underestimates the true model in this region. Okay, the green line, however, it fluctuates quite a bit from one random data set to another, right? For this particular data set at 1.5, it's way above the line, okay? For this particular data set for 1.5, it's below the line. And for this data set at 1.5, it's right on the line, okay? So we get quite a bit of variation depending on the random data set we have. So we have high variance, okay? However, if we say, take a look at this line at 1.5, we get one is below, one is on average, one is above, okay? On average, we're probably going to get the true value, okay? Probably going to get the true value. Oh, I am running out of time. Okay. So, well, I guess you're going to have to read some of these slides on your own here. That's how we would kind of model this idea of a bias and variance for regression data. For classification data, okay, we just kind of say, all right, do we get the category right? If the true category is A, how often did I get A? Okay, if the true category is A, did I get 100% right, 90% right, something like that? That's kind of the error classification rate, okay? And so here is, we'll look at some the k-nearest neighbors classifier later, okay? And here I've got this data here, right? This is the training data in these circles, right? And this is kind of the boundary it draws. And if I say, okay, well, based on some test point, would this be orange or blue or something like that? And so these are just basically different options, possibilities. And you can have kind of this highly flexible model with k equal to 1, okay? Or you can have a very low flexibility model, okay? And here the true boundary is then this dotted purple line, okay? The true boundary is in this dotted purple line. And when you have k equal to 100, you have this not a great boundary, okay? It loses this whole kind of, I don't know, peninsula in the region here, okay? But when you have k equal to 1, you have, these weird things where you get these little islands just because you had one observation that was kind of out of place, okay? And so, we're looking for something kind of in between. Okay, I've run out of time, but basically, I will post some data camp homework. Okay, first of all, make sure the email address that UCLA has for you is your correct email address. And I'm going to send out data camp invitations. And you have to check what email was invited, and you have to create an account with data camp with that email. Because if you use the wrong one, it's not going to work. So some of you, if your name is Miles Chen, or your email is mileschen@ucla.edu, at DataCamp, you have to use mileschen@ucla.edu. If it's mileschen@g.ucla.edu, at DataCamp, create it with mileschen@g.ucla.edu. If you create it with the wrong thing, DataCamp doesn't know that at g.ucla.edu and at ucla.edu goes to the same person. They don't know that, okay? You guys know that, but DataCamp doesn't. So I'm going to use whatever email address is listed in the course kind of roster. And if that's at g.ucla.edu, use at g.ucla.edu. If it's at ucla.edu, then use at ucla.edu. Don't mix it up, okay? I have a certain number of invitations to give out. And if you sign up with the wrong thing, it's not going to work, okay? So make sure you use the correct one. Okay, last view quiz answer is the letter D. Okay, so question 4 is the letter D. D as in dog. D as in dog. Okay, I will give you some homework, and then we'll introduce tidy models. We ran out of time today, But I'll assign some homework from data camp and some books. Okay. All right, looking forward to a great class with you this quarter, and thank you again to those of you who have your cameras on. That is, greatly appreciated, and we will see you on Wednesday. Have a great day.